All right, welcome back. Today we're going to crack open a classic computer science puzzle. It's one of those really elegant, super clever problems that's all about working with tricky constraints and finding a brilliant solution that, at first, seems kind of impossible.
Okay, so to get started, let's talk about our main player here, the linked list. The best way to think about it is like a chain of clues in a treasure hunt. You're standing at one clue, a node, and it only tells you where the very next clue is. That's it. You can't skip ahead, you can't go backward, and most importantly, you have no clue how long the chain is until you've walked the entire thing. That's the real challenge.
So now that we're on the same page about linked lists, let's set up the specific puzzle we're going to solve today. So here's the mission. You've got a linked list and you're given a number. Let's call it n, say 3. Your job is to add up the values of the last 3 nodes. But here's the catch, the big constraint. You are only allowed to walk through the list one time. And right away, you can see the problem, can't you? How are you supposed to know where the last 3 nodes begin if you don't even know where the list ends?
Now, before we get to the really slick answer, let's talk about the first solution that probably jumps out at you, because understanding why the obvious answer doesn't work here is half the fun. So the most straightforward thing to do is just take 2 trips, right? First, you walk the entire list just to count how many nodes there are in total. Let's call that length L. Then you do some simple math, L minus N, to figure out where the summing needs to start. And then you go all the way back to the beginning and walk the list a second time until you hit that starting spot. And from there, you add up the rest. It makes perfect sense, it works, but yeah, it breaks our one big rule. We're only allowed to go through it once. So that 2-trip solution, as logical as it is off the table. That means we need to get creative. We need a trick that lets us find our starting point without knowing where the end is. And that is where this super clever technique comes into play. You'll hear it called the 2-pointer technique, but I really like to call it the head start trick. It's all about using relative distance to your advantage. We're going to use 2 markers, or pointers, to walk through our list. Let's give them names. We've got a lead pointer and a trail pointer. Think of the lead pointer as our scout. Its only job is to run ahead and find the end of the list. The trail pointer, on the other hand, is the one we really care about. Its job is to lag behind just enough so that it lands perfectly on our starting line.
So picture this. You've got 2 runners on a track. We tell one of them, our lead pointer, hey, you get a head start of n steps. After it takes that head start, we yell go, and from that moment on, they both run at the exact same speed, 1 step at a time. Because of that initial head start, the gap between them is always going to be n steps. This is one of those things that just clicks when you see it. So let's walk through an example and see this trick in action. All right, check this out. Here's our list, and we want to sum the last 3 nodes, so n is 3. Both of our pointers, trail and lead, start right at the beginning at the node with the value 10. Now for phase 1, we only move the lead pointer. We give it that 3-node head start. 1, 2, 3. So now our lead pointer is sitting on 8, while our trail pointer is still back at 10. The gap is set.
Okay, phase 2. Now things get interesting. Both pointers start moving together, in lockstep. The lead pointer hops from 8 over to 2, and the trail pointer takes its first step, from 10 to 5. You see? The gap between them is still exactly 3 nodes. Let's do it again. They both take another step forward. Lead lands on 12, and trail lands on 8. They're just moving in perfect sync, always maintaining that crucial 3-node gap. And one final step. The lead pointer hits that last node, the 3, and at the same exact moment, the trail pointer lands on 2. Our lead pointer has reached the end of the road. It has nowhere else to go.
And boom, that's the whole trick right there. Just look where our trail pointer is sitting. It's pointing right at the node with the value 2. Because we kept that constant gap of 3, the very instant our lead pointer hit the finish line, our trail pointer was perfectly positioned at the start of the last 3 nodes. Pretty clever, right? Okay, that's the logic, and it's pretty cool to see visually. But how does this actually look in, code? Let's take a look at how this all translates into C.
So we're going to break this down into the exact same phases we just saw. First up, giving our lead pointer that head start. This is just a basic for loop, nothing too fancy. It just runs n times, and each time through, this line here, leadPTR equals leadPTR.next, just nudges the lead pointer 1 step forward. We also have a little safety check, just in case the list is actually shorter than n. If we fall off the end while we're trying to set the gap, we know something's wrong and we just return an error.
All right, Head Start is done. Now for phase 2, where they march along together until the lead pointer finds the end.
For this, we use a while loop. And the condition is super simple. As long as the lead pointer hasn't fallen off the end of a list yet, we keep going. And inside the loop, we just do two things. Move the lead pointer forward one step and move the trail pointer forward one step. That's it. That's how we keep them moving together.
And as soon as that loop finishes, it means our lead pointer has finally hit the end. And that means our trail pointer is parked right where we need it. Time to do the actual math. And this is the easy part, really. It's the whole reason we did all that work. We just start another simple while loop, this time using our trail PTR. We add its data to our total sum, then move it to the next node. And we just keep doing that until we hit the very end of the list. And that's it. We've summed the last n nodes in one single pass.
So, look, the big takeaway here isn't just about summing the tail of a list. This lead and trail pointer idea is a fundamental pattern, a real tool you can put in your toolbox for all sorts of linked list puzzles. So I'll leave you with this question. Now that you have this powerful pattern of setting a gap and moving in lockstep, what else could you do with it? What other tricky list problems could this simple idea solve? Think about it.